Okay, so my name's Buck, and I did my senior project modeling a damped static pendulum using different numerical integration methods. So first, give a little outline. What is all that? What is it? Why model it? How is it modeled? Implementations that I did, the results that I found, and ultimately, what did I learn in the process? That was my main goal for picking this project, is trying to maximize learning the things I wanted to learn. So first, what is it? It's a pendulum that can move freely in the XY directions, but it's bound in the Z direction by the length of the pendulum. There's three distinct forces that act upon it: gravity, attractors, and some sort of air resistance or dampening force. The attractors are treated as fixed points that exert a force proportional to 1 over the distance squared. And it's modeled using differential equations and solved using numerical integration methods. So why model it? The problem is relatively generic, so all of the coding and math that I learned in the process is very applicable to a range of different problems. Anything involving differential equations, which is fluid dynamics, any sort of kinematics, all of those kinds of things. The problem is computationally intensive, making an interesting problem to work on to optimize both mathematically and programmatically. And this is actually the problem that is first introduced for the final project for Physics 381. But the implementation we used was quite slow, taking hours to generate just a single image. And so it was, for all practical purposes, useless for real system analysis. And the images formed create this chaotic fractal pattern, which you'll get to see, which is really pretty. So that added bonus. So here's a picture for a magnetostatic pendulum. And in this case, your attractors are essentially permanent magnets. They're attached to a plate. And above that, there is a pendulum suspended. And the pendulum head is attracted to each of these fixed magnets. And the base plate is acting as our XY plane. And so you can see that it is bound in the Z direction by this length. And the problem that I'm modeling is for a generic static fixed attractor system. So in this case, you have magnets. There'd be a special kind of math for that. If you had some sort of point charge or varying force or whatever it would be, you just adjust the equations based on that. I'm taking the simplest case. And so here you can see on the right are a couple of just simple free body diagrams to figure out what the forces acting on the pendulum are. And what we have are the force due to gravity from these equations, the force due to the attractors from these, and then some dampening force. And what we're doing is simply applying Newton's force is equal to mass times acceleration. And the acceleration is the second derivative of position with respect to time. And so this is where differential equations come from. We just sum up the forces divided by the mass, and that's the second order with respect to position. And we do that for both the x and y. And I'm not going to get into this too much in detail, but essentially this is the numerical formula for how you actually solve these types of systems of differential equations. So this is one particular method. It's an adaptive Runge-Kutta method, specifically this Cash and Karp method. And so these are coefficients for the numerical algorithm. And essentially you go through these different stages, multiplying through by these coefficients for every step you take. You then get two different order solutions. One is more precise than the other. You compare the difference, and then you're able to adjust your step size based on that. All right, so plotting the system. How do we do it? We take the pendulum head, we pick some position in the XY plane, and we release it. And those are the initial conditions. The pendulum swings according to all the forces mentioned, and then the pendulum eventually converges and comes to rest at one of the attractors due to the dampening or air resistance. So here's a plot kind of showing this. So these are our starting points. For example, here you have -2, -3, and we're looking at this XY plane, essentially the base plate. You bring the pendulum to this point, you let it go, and it takes some very interesting trajectory path that you solve using the numerical integrator. And eventually it'll come to converge at one of these attractors, which is represented here in red. And so you can see for the magenta one here, it converges to this lower right attractor, and for the cyan one, it converges to the attractor on the right. So now we can use this information to now plot an entire map of starting positions. And we do this by finding the converge point for a set of starting points, equally spaced across the entire XY plane that's only bound by the length of the pendulum. We assign a color to each starting position according to the attractor it converges to, and then we just continue to decrease the space between these starting positions to try to form a continuous image. And essentially each starting position represents a pixel on our image. So here's what it looks like when you do this. So for some set of parameters for the gravity and air resistance, etc., you end up with this map. And this is for a pendulum where the length is 10, and that's why it creates this circle. And so the white is outside of the bounds, and all in here is inside of the bounds that we can look at. And so to get a sense of what's happening here, each of these colors represents an attractor. And so if we start the pendulum right here, anywhere in this blue region, it will converge to this blue attractor here. And then we're doing that for all of the attractors. So 3 different implementations to do this. Starting with the Mathematica using ND-solve. This is the method that was implemented in Physics 381. And you can actually trace and figure out what kind of the underlying method is. It's just this multi-step method. So then I started with Python, just using some simple open source science and math libraries, NumPy, SciPy, and sped it up using Numba. And that was a little bit faster, but I want it faster. So then from the ground up, writing in C++, using this embedded adaptive step size method by Cache and Carp that I showed earlier. And so why 3 different implementations? So this gives a sense of computation times relative to one another. So for the Mathematica method that we implemented in 381, it takes about 15 seconds to do a sample map that's 841 starting points, which would be a 29 by 29 pixel image. And this is on an i7 laptop machine. Next, we implement the implementation in Python. It's about half that time. And finally, with the C++ method, we're able to get about a tenth of a second. So it's about 150 times faster for generating these plots. So why do the computation times matter? So we want to construct a bunch of these high-resolution maps to get a sense of how the system behaves when you vary parameters, gravity, air resistance, all of those things. And an 800 by 800 pixel map takes about 2 hours and 30 minutes using Mathematica, and it takes about 1 minute using the C++. So obviously, a concern is the precision and numerical stability. How do we know we're integrating the points correctly? Did the implementation I create actually do it correct? So I just did a quick check, sanity check here. Basically, took a fairly high resolution map, 800 by 800, which is 640,000 points, and I compared them between Mathematica and C++. Initially, they disagreed. 1,500 points out of those 640,000 disagreed. So I reran the integration on the points that disagreed in Mathematica, using just simply a more strict error control. Then only about 25 points disagreed. Finally, I went back to the C++ implementation, made it more strict on the error control. No points disagreed. So I at least know that the mathematical integration I'm using in C++ is correct, at least according to Mathematica. So we can zoom in on some of these regions. We get to kind of see this interesting fractal type image. And so here, we originally were seeing sort of that 20 by 20 square. And now we're looking at a, this is 2.5 along the x. This is 0.5, and this is 0.05. So we're really zooming in now. And what you can see are, there's these stable basins, and then in between, there's these lines of other areas where it will converge to a different attractor. And so it's very chaotic in the sense that a small change in one of these initial starting points will completely change the attractor it converges to. So here's another map. This is the same system we were looking at before, but with about 20 times the gravitational force. And the black represents the boundary for the system. And basically, all inside here where you don't see a color, it actually converges to the center. So basically, what's happening is we can see that gravity is dominating this system. And most of the points end up going to the center rather than one of the attractors. This is another one I did just to kind of show you can do it with 4 attractors in different positions. And I thought this one was really cool, kind of blending physics and art. Got to kind of see some interesting patterns that emerge from this 4 attractor system. So with this enhanced computation times, we can actually generate animations to get an even greater sense of how the parameter changes influence these maps. So what we do is we integrate mini maps with slightly changing parameter. In this case, it was 500 to 800 by 800 maps. And it would have taken weeks of continuous computation using the Mathematica implementation. And it took approximately 5 hours using the C++ implementation. And in this particular case, the one I'm going to show you is the animation starts with a weak dampening force. So the coefficient's around 0.1. You can think of this as like the pendulum's in a low-density gas. And then we gradually increase to a very high dampening where the coefficient's 0.5. You can think of the pendulum being suspended in a viscous fluid like oil or water. And show this. So it starts very, very chaotic. It's sort of speckled. And as we increase the dampening, you can see how it morphs. So essentially, the map becomes more and more stable, and you don't end up with all the speckled regions. It's nice, big, stable basins. So I just want to mention the code is open source. The C++ implementation is freely available on GitHub. It's completely modular and object-oriented, so the integrator, the system, and the map are completely separate and easy to interact with. So for example, if you want to add another attractor to the system, it's as simple as just calling some function, giving it an x position, a y position, and an attraction strength. It'll add that to the system. When you go to generate the map, it'll generate the map according to that. You can set the colors for all of the attractors, all of that kind of thing. So it's easy to add more integration methods and other systems of differential equations, and documentation for this API is in progress. So concluding remarks, I learned about differential equations, numerical integration methods, programming different languages, and optimization techniques. This is why I picked the project. It was very interesting to me. I enjoy all these things. Successfully decreased the computation times by more than 2 orders of magnitude. Utilized improved computation times to create the animations to start to get some visual understanding of how the system behaves. And the code can be expanded by adding statistical analysis tools, new physical systems, and more integration methods. And finally, I just wanted to mention that there was a paper published recently by a group of physicists that quantitatively categorizes these types of damped chaotic systems. And they call it doubly transient chaos. And essentially, transient chaos is the system starts, you don't know where the attractor is going to go. Eventually, it converges to one of the attractor. It's no longer chaotic. Doubly transient, it's damped, which means over time, the trajectories away from the attractors decay super exponentially. So some interesting math behind that. I'd like to say thanks to Hung Tao Shi for giving me feedback on organizing such a short presentation, Hunter Mills for the geometry of our free body diagrams, and Mike Jones for originally getting me interested in the